Cool. Hello, everybody. My name is Clint van der Venter, and I'm going to be doing the grade 10 physical sciences lessons for the next few weeks. I hope that what I have to share with you will be informative and helpful. And please, I'm happy to answer any questions that you might have. So feel free to just perhaps interrupt me. I would hate to be explaining stuff and then you guys are not following. So yeah, let's get down to it. We're going to start. I've been asked to start with term 3 and term 4 work. So I'm going to start with the first section in term 3, which is reactions in aqueous solutions. And this section is really about, there's a bit of theory to it and if you spend the time going through the theory, just studying the few rules that there are and learning the definitions, then it could be a topic in your paper 2 exam. So this is chemistry. This could be a topic in chemistry that you do quite well in. The most important skill you need is, and what you will learn here hopefully, is to write chemical equations that happen in aqueous solutions. And this will help you in grade 11 and in 12, and then obviously for grade 10. So let's get down to it. Oh, sorry, just before I start. So term 3 work, there's also a good chunk of chemistry that we're going to be doing, stoichiometry, with all the calculations. That can be quite difficult for grade 10 learners. So we'll probably start that next week, depending on how far we get on this week. And then we've also got mechanics to come, which is also lots of calculations, lots of equations, and sometimes tricky for learners. So I hope that you really will benefit from these lessons. Okay, let's get going. So reactions in aqueous solution. Many reactions in chemistry and all biological reactions, so those are reactions that happen in living systems like animals or plants, okay, take place in water. And that's what we mean by aqueous solution. Aqueous solution simply means a chemical reaction that happens in water. Water is unique, and although it's everywhere and we take it for granted, it is actually very special chemical substance. And you know, when people are always moaning about, oh, don't drink this, there's chemicals in it, don't drink that, there's chemicals. Well, water is a chemical, and it's such an amazing chemical. All life depends on it. So it's really important. And we're going to talk about the molecular structure of water and what makes it so special. And then we're going to look at the 3 types of reactions in aqueous solution, which means reactions that happen in water: precipitation reactions, acid-base reactions, and redox reactions. And I will explain all of those when we get there. But first, I didn't want to go straight into this. I wanted to check that that everyone is on the same page with regards to some important chemistry basics that we should know and understand, because you're going to be writing chemical equations and you're going to be dealing with ions, and we need to just make sure that we understand some of the basics. So, do you remember learning about covalent compounds? This is between a non-metal, which is on the right-hand side of the periodic table, and a non-metal. So any 2 elements or atoms on the right-hand side of the periodic table. And I do have a periodic table here that I can just bring up. Okay, so these are the metalloids, generally these sort of greeny ones. And anything on the right-hand side are non-metals, and anything on the left-hand side are metals. So that's how we know if something is a metal or a non-metal. And we know that metals look a certain way because they're shiny, etc., and non-metals can be powdery, etc. So covalents are non-metal and non-metal. A covalent bond forms between non-metal atoms, and that is when we share electrons. Okay, so that is some important chemistry basics. And we call covalent compounds, we call them molecules, generally speaking. So when you're talking about a molecule like the water molecule, it's a covalent molecule because it's made from hydrogen and oxygen, which are non-metals. And an example of a covalent compound would be sugar that you put in your tea. Right, ionic compounds. This is a different type of compounds and very important for this section of work that we're going to be doing, because we're going to be mainly dealing with what ionic compounds do when we put them in water. So ionic compounds are between metals, which are on the left-hand side of the periodic table, and a non-metal, which is on the right-hand side of the periodic table. Okay. Between a metal and a non-metal, that's where we get an ionic bond. And sorry, that's not where electrons are shared. This is where electrons are transferred. Okay, electrons are transferred when we have an ionic bond. So we get a positive ion and a negative ion. If I lose a positive, if I lose an electron, remember, chemical bonding is all about your valence electrons and which valence electrons you might accept or give away. And if I give away electrons which are negative, then I become more positive. And if I accept electrons which are negative, then I will become more negative. And we're going to talk about that just now. So ionic compounds are often called salts. So covalents are often called molecules. Ionic compounds are often called salts or crystals. Now we know the word salt as the salt in our cupboard, which you put on our food. That is one type of ionic substance. That's sodium chloride, which you have. It's called table salt. That's the common name. But you get many different types of salts. And that is any ionic compound like copper chloride or calcium chloride or magnesium chloride or magnesium sulfate. Those are all different ionic compounds. Okay. I spoke a little bit about this, but just to remind you, so the valencies are also important because if we're going to be writing ions, we need to make sure that we remember how the valencies of an atom might work. So this is group 1, the first column on the periodic table. That means there is one electron in the atom's valence orbital, which means the outer orbital. So that's the electron that atom is going to use to make a bond with another atom. Okay, valence electrons, it's got other electrons, but there's one outer electron, which is the electron that is important for bonding with other atoms. In group 2, we've got 2 valence electrons. In group 3, we've got 3, and in group 4, we've got 4. And then 5, and then 6, and then 7, and then 8. Okay, so in group 8, the valence orbital can only take 8 electrons. So in group 8, that group is full. Okay, they don't need any other electrons. That's why these elements are called the noble gases, because they are stable. They don't want to react with any other atom. They don't want to share electrons or transfer electrons because they are happy with their valence orbital. Okay. So while the +1 and the +2 and the +3, etc., and the -3 and the -2 and the -1, well, if I only have one electron, then it's easy to give away one electron. And if I give away one electron, I will become positive. Okay. Whereas if I'm in group 7, if I'm an atom in group 7, I already have 7 electrons. Now, remember, to get a full valence orbital, which is what an atom wants to do, I need to have 8. So it's easier to get one electron than to lose 7 electrons. So if I'm in group 7, I would rather gain an electron, and that's why we have our valency of -1. Okay. And in group 2, you have 2 valence electrons, so you give away 2 electrons. It's easier to give away 2 than to find 6, okay? Because remember, we want to have 8. If you're in group 6, then it's easier to find 2 electrons than to get rid of 2 electrons. So that's why if we add 2 electrons, we're going to become -2, okay? And that's how the valency works. I don't want to go through each one, but please stop me if you don't understand what I'm saying. But that's why we have in group 5, we've got -3 as our valency. Group 4 is special because these have 4 electrons. They can either gain electrons or lose electrons. That's why elements in that group are so versatile, particularly carbon. And it's a whole sphere of chemistry on its own called organic chemistry, because carbon can just make so many different molecules. So that's the atom valency, which is important for what we're going to do in this section. Okay. Another important skill that you need to already have is how to write ionic compounds. Okay. Remember, it's a non-metal and a metal. Now, generally, the metal is always a cation, meaning that it's positive because it comes from the left-hand side of the periodic table. And if you look here on the left, all of these ones on the left, okay, they all have +1 valency or +2 valency or +3 valency. Even these transitional metals, they all generally have a plus valency. They're just called transitional because sometimes they have +1, sometimes they have +2, sometimes they have +3. It depends, and we will get told what it is. So metals generally have a valency of plus because they're going to give away electrons, but non-metals are going to have a valency of minus. So these ones here, because they're going to accept electrons. Okay, so we call a positive ion a cation and a negative ion an anion. And we're not talking about iron as in the iron you use to iron your clothes with, or the metal ion. We're talking about ION. Okay. That means an atom that has lost electrons or gained electrons to get a positive charge. So when we need to write a compound, say calcium chloride, I don't tell you what the formula is, okay? You've got to know how to write the formula. So how do you know it's CaCl2? Well, you go to a periodic table, you look for calcium, it's in group 2. That means it has a valency of +2, okay? So calcium is going to be +2. And then chloride, you go look, okay, where is chloride? Okay, let's clean this all up a bit. That was calcium. Let's look for chloride. It has chlorine, okay? It's in group 7, so it has a valency of -1. And it helps to write these valencies on your periodic table. Okay, and then now when you write it, you've got to balance out your positive and your negative charges. So we've got our Ca 2+ and our Cl1-. Now, with the Ca, we've got 2 positive charges, and therefore we need to have 2 Cls. Okay, because both these 1- are going to balance with this 2+. Hence, we get the formula CaCl2. So there's 2 chlorines for every 1 calcium. Okay, that's the theory behind it. The very quick way to always write down your ionic compounds. Sorry, I like to say 2+ and 1-. Doesn't really matter. Is to do this. You might have seen your teacher teaching you like that. Okay, you do your little crisscross method. So that because there's going to be 1, you drop your positives and your negative. So you're going to have Ca1 and Cl. You're going to take this 2 and you're going to put it over there. And then, of course, just like in maths, we don't write the 1. We just leave it. CaCl2. The 1 is invisible, like I always say in my maths classes. We don't write 1x, we just write x. Okay, so that's how we write ionic compounds. And we can maybe just do 1 or 2, maybe one other example. Yeah, let's do the second one. So this is barium, okay? And it's in group 2, so it has a valency of +2. And we get that from the periodic table. You won't be told what the valency is. You need to go to periodic table and see what group it is and then choose the valency. Then we've got oxygen. So when barium and oxygen come together, okay, oxygen is group 6, so it's going to gain 2 electrons. So it's got a 2-. Now when we do our little method and we do our swappy, we're going to get Ba, strictly speaking, Ba2O2. But that simply means that for every 2 baryons, we have 2 oxygens. And then the simplest ratio would mean that, of course, then for every 1 barium, we just need 1 oxygen. Because that ratio is 2 to 2, we can just simplify it as into 1 to 1. So that's why we write BaO and we don't write Ba2O2, just because we're simplifying the ratio. Yeah, and then there we go, this one. We're going to take that 2 there, we're going to take that 1 there, and hence we get our K2S. And for this one, we're going to take our 1 there and our 3 there, and we're going to get our FeBr3. That means that there are 3 bromide ions and 1 iron. Fe is iron. And that last one, you're going to take your 2 there, and you're going to take your 3 there, and that we get Cr2. So 2 atoms of Cr to every 3 atoms of oxygen. So this is really important. You need to be able to write the formulas for ionic compounds before you can do this section of work. I suppose I should have just left that on there. Okay, and then remember your compound ions, because this process gets a little bit more complicated, because a metal can also bond with these compound ions. A compound ion simply just means that it's not a simple ion that consists of 1 atom. It's an ion that consists of different types of atoms, like ammonium. You can see it consists of N and H, so nitrogen and hydrogen, and nitrite is nitrogen and oxygen, etc. Bisulfate is hydrogen and sulfur and oxygen. Okay, so these have special names and they have special formulas, and unfortunately you guys have to learn them. Okay, you just need to learn the common ones, and if you ask your teacher, I'm sure they'll tell you what it is. But it's ammonium, it's nitrite, it's not salt, bisulfate, hydroxide, phosphate, it's almost everything. The hydrogen phosphate and the dihydrogen phosphate don't come up too often. Carbonate, bicarbonate, even the chlorates and chlorides don't come about too often. Dichromate you see sometimes. So those are really the common ones that you should spend your time learning. You've got to learn the name, and you've got to learn what the little formula is with its little valency. So carbonate is CO3, 2-. So this is an ion. You don't just get carbonate by itself. Carbonate will always be bonded to another metal atom, okay, to form an ionic substance like calcium carbonate. Okay, so for example, if we have calcium carbonate, that means we've got calcium, and that means we've got carbonate. So you need to know off by heart that carbonate, so you need to, first of all, if you read calcium carbonate, you've got to identify that word carbonate as not something that you find in the periodic table. There's no carbonate in here because it's a compound ion. The periodic table only contains single atoms. Compound ions is different, and you've got to be able to identify carbonate as CO3, 2-. Okay, then calcium you've got to be able to identify as just being in your periodic table in group 2, so its valency is 2+. So when I do my little swappy, then I'm going to get Ca2, CO3, 2. Now my pluses and minuses drop away. And this is the same instance that we spoke about earlier on, where for every 2 calciums, there are 2 carbonates. And look how this carbonate is in brackets. Okay, because that is like one thing. It's the compound ion. So if I need 2 carbonates, then I need 2 of those whole formulas. So you should just put it in brackets always. If you don't put it in brackets, it's going to be wrong. And it won't make any sense. So we will write that as CaCO3, because for every 1 calcium, well, for every 2 calciums, we need 2 carbonates. And if we simplify that ratio, 2 to is the same as 1 to 1. But let's just do one more little example that might be a little bit more complicated to see if you can understand it. So I have written down one that I thought might be a good one. What about ammonium sulfate? Okay, ammonium sulfate. So you need to be able to identify that the word ammonium is not in the periodic table. It is a compound ion from your compound ion table, which you need to know off by heart. So ammonium sulfate will have NH4 plus, because it's an ion, cation. And then sulfate you need to identify as also not being on your periodic table. So don't get confused between sulfate and sulfide, because sulfide with a D, we're talking about the sulfur ion. Okay, when sulfur accepts 2 electrons, you get sulfide. But sulfate, and you also have sulfite, it's very similar, and you must make sure you can remember the difference. So sulfate will not come from the periodic table, it will come from your compound ions, and then you got to know that the formula is SO4 2-. And the more you work with the stuff, the more you get to know these formulas. And before long, you're dealing with them without even thinking. So what does that tell us? There's a 2-. Let me do it the long way, just for fun. That's the 2-. So there's 2-, and then there's 1+. So I need another plus to balance it out. Okay. Now my charges are balanced. Now they're going to be neutral because I'll have 2 pluses, and on the right-hand side, I've got the 2-. So for every 1 sulfate, I have to have 2 ammoniums. So there's ammonium sulfate. So the ammonium should go in brackets because there needs to be 2 of them. And if I did it just that little quick way that I showed you, you can put your 2 there and your 1 there. Remember that plus just means it's a +1. The 1 is invisible. So if I'm putting my 2 down over here, that means I have to have 2 ammonium ions for every 1 sulfate ion. Are there any questions about writing a ionic compound using compound ions? Because I know that students do find this difficult sometimes. Okay, please don't be shy to stop me and ask me. I hope I'm not boring you and telling you stuff that you already know, but I'm just making sure we're all on the same page. Otherwise, this work, which is actually quite easy, this chapter, it will be difficult if you don't understand the basics. And then, of course, the last skill is balancing reaction equations. So we write a reaction equation whenever there's a chemical reaction. As you know, on the left-hand side of the reaction, we call them the reactants because they are reacting. And then on the right-hand side, the reactants react to form the products. And we get the product. So that's the language that we use, okay? And of course, in every chemical reaction, this needs to be balanced. The atoms need to be balanced because you can't, like example here, you can see that there's 2 oxygens on the left-hand side and there's 10 oxygens on the right-hand side, okay? That's impossible, okay? Because you can't start with 2 oxygens and then suddenly there appears 10 oxygens. We are talking about the conservation of mass principle. So whatever we started with is whatever we have to end with, and that's why we always have to balance equations. So you can see this 4 here, it's now an attempt to balance because before that 4, there was 2 hydrogens on the right and 8 hydrogens on the left. There's my 8 hydrogens. And then I added the 4 on the right-hand side. And whenever you balance equations, it's the coefficient in front. So for example, H2O, if I put a number there, that's called the coefficient. Whereas this little 2 here, that you can't ever change. You can't add little twos or take them away. That is what we call the suffix. No, what is it called? I've forgotten the word. I'll think about it just now. But yeah, those little numbers you can't change. So that stays the same. So whenever you're balancing, you're adding a coefficient in front of the molecule or the formula. So we put a 4 in front of the H2O, and that means now we've got 4 H2s. 4 H2s, so that means we've got 8 altogether now. 4 H2s, that means we've got 8, which now balances with this 8. Hooray. Let's look at our carbons. We've got 3 carbons there. If we put a 3 in front, we can have, of the CO2, we can have 3 carbons. Hooray. Okay. And if we have the 3, then we've got 6 oxygens. Plus we've got those 4 oxygens, which makes 10 oxygens. Okay, because there's 4 oxygens, because 4 H2O means that there's 4 H2s, which means 8 H's, and there's 4 O's. So this is not quite balanced. We would need to balance it because look, our oxygens are still not balanced. So what do we need to do? We need to put a coefficient in front of the O2 here. So I need 10. So I should put a 5. I should put a 5 there so that I can have 10 oxygens. And then it will be balanced. So my final equation will be C3H8 plus 5O2 gives you 4 H2O plus 3 CO2. And that would be my final balanced equation. So it's very important to have balanced equations when we are dealing with chemistry and chemical reactions. Okay, so let's get on to the actual new work that we need to learn. Okay, so we need to talk about how amazing water is. Okay, it's all around us, but it is really amazing. Without it, life wouldn't exist, as we said before. Water is seldom pure, okay, because there are often substances that are dissolved in it. I think sometimes we don't think about that a lot. There are lots of liquids that you can't dissolve other things in. For example, if you look at oil, you can see things that are in oil very clearly, and you could then go and filter it out. Because if something falls in that oil, it doesn't really dissolve. It's a very difficult thing to dissolve. Whereas water, I mean, yes, sometimes you can see that water is dirty, but there's often times where water might look pretty clear, but there's lots of things that are dissolved in it that you can't see. And if I gave you a cup of sugar water and salt water, you wouldn't be able to tell the difference just by looking at it. And obviously, if you tasted it, you would. But that just shows you that water looks the same, but there's different things dissolved in it. And water is quite amazing in that things can dissolve in it. And that's what this whole chapter is about. It's about things or chemicals or salts dissolving in water. Okay, life would not be possible on Earth if that couldn't happen. So why is water so amazing? It's because of its molecular structure. So you might be asked to explain why water is amazing. Okay, it's because of its molecular structure. So go ahead and speak about the molecular structure. Okay, we know that water H2O is made up of oxygen, which is in group 6 of the periodic table. That means it's got 6 valence electrons. 1, 2, 3, 4, 5, 6. Okay. And then it's made up of 2 hydrogens, and hydrogen is in group 1 of the periodic table, and it only has 1 valence electron. Okay. Now, hydrogen and oxygen is a non-metal and a non-metal. So when they bond, when these atoms bond, they're going to form a covalent bond, which means they're going to share electrons. So here we go, we share, and there we go, we share. Okay, so oxygen, remember, oxygen needs 2 electrons. So now oxygen is happy because it's got 8 electrons around it. There's 2, and there's 4, and there's 6, and there's 8. Okay, so oxygen is happy, and hydrogen is also happy. Hydrogen is the one metal that only needs two electrons in its valence orbital. But what's special about this bond is that oxygen, and generally it doesn't actually happen like that. Generally it happens more like this, where we have, where's my purple? We have it like this, hydrogen over here and hydrogen over here, okay? So we might remember learning in term 1, I think it was, about electronegativity. Electronegativity means that an atom likes to keep the electrons that it shares nearer to it than it does to the other atom. So for example, you can imagine sharing a chocolate with your baby brother or your baby sister, okay? And he has the chocolate, and what are you going to do? You are more chocolate electronegative, so you're going to pull the chocolate towards you, and because you're bigger and stronger, the chocolate is going to be closer to you, and your poor little brother and sister, the chocolate is going to be far away from them in relation to how close it is to you. So it's the same kind of concept with these electrons. The oxygen pulls these shared electrons, so these are the ones that are shared, it pulls these shared electrons more towards it, okay? Which makes, so here's a nice diagram, because oxygen now has lots of electrons around it, and hydrogen has only a few little, like 1 or 2 little electrons around it, but they are far away from it because oxygen is pulling them towards itself. The oxygen molecule is going to be partially negative. Let me get a partially negative. And the hydrogen, not the oxygen molecule, the oxygen atom is going to be partially negative, and the hydrogen atoms are going to be partially positive because they have so few electrons around them or close to them, and oxygen has lots. And if you've got lots of negative around you, you are going to be negative. And we say it's partially negative and partially positive. So we use that funny little SC kind of symbol, it's a Greek letter, to just mean partially, because oxygen is not completely negative, but it is more negative than it is positive. So it's partially negative, and hydrogen isn't completely positive, but it's more positive than it is negative because oxygen is pulling all the electrons towards it. So because of this positive and negative relationship, it means that oxygen is what we call water is what we call a polar molecule. Okay, think about the poles of the Earth. You have the North Pole, and then you've got the South Pole. Okay, and it's the same concept. If a molecule is polar, it means there are poles. There's a North Pole and a South Pole, except not a North Pole or a South Pole, but a positive pole and a negative pole. So on this side of the water molecule, this one side of the water molecule is more positive, and the other side of the water molecule is more negative. So that's why it's called polar, because it has poles, a positive pole and a negative pole. Whereas a lot of molecules are not polar. They don't have a side that is more positive and a side that is more negative. And because water has this, and there are other substances that that are polar, but because water is polar, it makes it very special. It means that a lot of things can dissolve in water, and I'm going to explain to you why. You will also see that it's called a dipole, which is the same kind of word. Di means two, so dipole simply means that there are 2 poles. So we can say it's dipole, or we can say that it is a polar molecule. So in short, why is water amazing? Chemically speaking, okay, not because it can support life. Why can it support life? Why is it so amazing? Well, because of its molecular structure, because of the way the electrons are arranged in the molecule. It is a polar molecule. It has one side that is positive, one side that is negative. And that means that a lot of substances, especially ionic substances, can dissolve in water, okay? Why ionic substances? Because remember, ionic substances, for example, NaCl, contains a positive ion and a negative ion, a cation and an anion. And that's why we did this little bits in the beginning here to really drum in the fact that we've got a positive ion and a negative ion, okay? So because of this positive and negative, and because water has a positive side and a negative side, there's going to be attraction forces at play. Positive is attracted to negative, and negative is attracted to positive. And that's why a lot of things can dissolve in water. And we are particularly going to be looking at ionic compounds in this chapter. So some terminology. Dissociation is a general process in which ionic compounds separate into smaller ions, usually in a reversible way, which means that they can separate like this Na and the Cl, and they can go back together again, okay? And normally when we have a reaction that does that, we use double arrows, okay? Sodium chloride can separate into sodium ions and chloride ions, and it can go back the other way to form sodium chloride again. Okay, sodium chloride is a crystal. Okay, and I'm sure if you've looked at salt before, I'm sure you can all imagine it in your mind. It looks a bit like a crystal. It's not very strong. You can easily break it if you squash it against the table. But we often call ionic salts. That's why I call them salts, because they look like crystals. So that's dissociation. Dissolution, okay, is when something dissolves, okay, and the ionic crystal, so the ionic salt, like NaCl, it breaks up into ions. But this almost sounds exactly like the previous definition, but this happens in water. So when we are dealing with water, we normally talk about it as being dissolution, okay. But you'll hear the words sort of interchangeably using dissociate. They kind of mean the same thing, except that dissolution just means particularly we're talking about water. And then the last little definition here, hydration, is the process where ions become surrounded with water molecules. And I'll show you a picture about that now. So here we go. And I believe that in many subjects, not just science, a picture can speak 1,000 words. So guys, I encourage you to when you're studying, when you're making your notes, to find a nice diagram to work on. Yes, you've got to study your definitions and you've got to do those calculations, but when you've got a picture to kind of guide you through it, it just makes it so much easier, and that's what you can picture in your examination. So let's look at this. Sodium chloride, which is a solid, that S there means that it's a solid. Okay. If it is dissolved in water, it will break up into sodium ions and chloride ions. So this is the correct way we would write the chemical equation, the dissolution equation or the dissociation equation. This S simply means that in the beginning, we put solid salt, so solid sodium chloride into the water. And this AQ means aqueous. Okay, it stands for aqueous. And aqueous is just a fancy word. Aqua, I'm sure you've heard of it. Aqueous means that it is now dissolved in water. Okay, so we don't put liquid there because it's not a liquid. It's a particle which is dissolved in water. So those are called state symbols, and we need to be able to write our equations with state symbols. So when sodium goes into water, there will be lots of these sodium ions, and there will be lots of these chloride ions. Okay, and what happens? Why does it dissolve so nice and easy? Because it gets hydrated by water molecules. So that's this process hydration that we spoke about, is when an ion becomes surrounded with water. So because sodium is positive, all the negative sides, this is the oxygen, that blue part of water, this is water. This is H2O here. All of these little blue and gray thingies, that's H2O. So because sodium is positive, all the negative sides of the water molecule, so the oxygen sides of the water molecule, surround this positive ion. Okay, and that is what hydration is. There, you just need a picture, and then then it's easy to understand. If you have to read this, then that might sound a little bit complicated. But if you look at the picture, it's easy. And the chloride ion is negative. Okay, so what does the little waters do? What do the H2Os do? They come the opposite way. The positive hydrogen sides come and surround, they get attracted to the negative chlorine ion, and that's what hydration is. So the negative side of water gets attracted to the positive sodium, and the positive side of water gets attracted to the negative chloride. And that's what hydration is. And that's why, and this is just an example of sodium chloride, but that's why a lot of ionic salts can dissolve in water. So what do you need to do with this information? Well, you need to represent this dissolution process using balanced reactions, okay? You need to define the terms that we just spoke about, and you need to explain how water is able to dissolve salts. So that is what we just spoke about, how water is amazing. It's amazing because of its molecular structure, okay, because it's a polar molecule. In normal life, we use the word dissolve and dissociate, dissolve a little bit differently. So salt water dissolves, salt dissolves in water, and it dissociates, which means it breaks up into ions, whereas sugar dissolves in water. That means it breaks down, it gets smaller, but it doesn't break up into ions. The sugar molecule, that's the sugar molecule, it just stays like it. It doesn't break up like the sodium breaks up into, sodium chloride breaks up into chloride ions and sodium ions. Okay, so there is a little difference there. I just wanted to point that out. I'm sure we've all seen this before, but I want to get down to actually the chemical equations. We can maybe talk about that later. But that's proof that water has a lot of stuff dissolved in it, because I'm sure we've all seen how this stuff happens in our bathrooms, etc. It's because there's lots of minerals in our water. If water was pure, that wouldn't happen. Okay, so for each, this is what you really need to do after this section. For each of the following, say whether the substance is ionic or molecular. So potassium nitrate, you need to identify that potassium as being a metal and nitrate as a compound ion. So it's a non-metal, it's made up of N and O, so it's a non-metal. Potassium is a metal, nitrate is a non-metal. So therefore it would be ionic, okay? Ionic. What about ethanol? Ethanol is made up of carbon, hydrogen, oxygen, and hydrogen. All of those things are non-metals, so therefore we call it molecular. There exists covalent bonds. In this one is covalent bonds, whereas in this one is ionic bonds. Okay. Sucrose, which is a type of sugar, it consists of carbon and hydrogen and oxygen. All of those are non-metals, so that's also molecular and not ionic. Okay, there would be covalent bonds there. And then sodium bromide. Sodium is a metal and bromide is a non-metal. So according to our definition, that is an ionic substance or a salt, and there would be ionic bonds there. Okay. So let's try write a balanced chemical reaction to show the following ionic compounds and how they dissociate. So sodium sulfate. So this is now where that knowledge of your ions come in handy. So this is how we would write it. We would say sodium sulfate, okay, which is a solid. Okay, it's a salt. It's an ionic substance. How do we know it's ionic? Because sodium is a metal and sulfate is made up of sulfur and oxygen, which is non-metal. So it's ionic. Okay, so this will be a salt, an ionic salt, just almost looking similar to actual salt. I think sodium sulfate is quite white. Okay, if we put it in water, now we don't say plus water here, okay, because it's not reacting with water. It's just getting put into water. So we're going to show how it dissolves, how it dissociates. It's going to dissociate into sodium ions and into sulfate ions, which are going to be aqueous, okay, because the ions dissolved in water, we call it aqueous. We don't call it liquid. AQ. But now we need, ions must have a charge. So is this a +1 or is it a +2? What is it? So sodium being the metal will always be positive, the cation. And that's when you go back to your periodic table and you go, look, which group is sodium in? It's in group 1. Therefore, it has a valency of +1. Okay. And then we spoke about sulfate. And that's when you know off by heart, sulfate is SO4, 2-. So that's how we know how to write the ions. So that's going to be a 2-. But now we need to check if it's balanced. We can't just move on. On the left-hand side, we had Na2. We had 2 Na. So we must also make sure we put a 2 there. We can't put it there. It's not going to go there. That would be incorrect. It's got to go in front because you only balance chemical equations by changing the coefficients. Okay. And we only had 1 sulfate ion there. There's only 1. So there is only 1. So we're going to keep it as only 1. We're not going to put any coefficients. And that would be our balanced chemical equation showing how it dissolves in water. Potassium bromide, we're going to have our KBr, which is going to be a solid. And it's going to be put in water and it's going to break up into its ions. Potassium ions and bromide ions. And whenever ions have dissolved, it's aqueous. So we use our correct state symbols. Now, how do we know what the valencies are? If these are ions, they need to have pluses and minuses. So potassium is a metal. And if you look in your periodic table, it's in group 1. Therefore, we know that this has to be a plus. And bromine is a non-metal. And if you go look at your periodic table, it's in group 7. So the VAT valency must be a minus. And then voila. That's how we write it. Let's do one more mouthful. Potassium is a metal, and permanganate, that comes from our compound ions. Okay, it consists of MnO4. So this is an ionic salt. So we're going to say potassium permanganate. They gave us the formula. It's going to be a solid salt, but I'm going to put it in water and it's going to break up into its ions. We're going to get potassium, which is in group 1. So it's going to have a positive valency, a 1+ valency. And then we're going to get permanganate, which is one of our compound ions, which is just going to be MnO4. Now, if you forgot what it should be, well, you can just check here. We were given the formula. And if this formula was KMnO4, that means the positive of the K has to balance with the negative of the MnO4. So we know that this should be a 1-. Or you can go check on your compound ion list. And is it balanced? Yes. For everyone, there's 1 K on the left, 1 K on the right, 1 MnO4 on the left, 1 MnO4 on the right. So it's important to know your compound ions because a lot of students, when they're doing this, they try and separate this MnO4. They try and make it all other funny things. But MnO4 must stay together because it is permanganate. So when potassium permanganate dissociates, it just dissociates into potassium ions and permanganate ions. So guys, I hope that was helpful and we'll carry on next time. Like I said, there's lots of theory to this chapter, but if you spend the time going through it, you can actually do quite well. All you really need to be able to do is write your chemical equations. And obviously, to be able to do that, you need to be able to write your chemical formula. So this will be actually a good revision for term 1 work where some of you might have missed out on how to do that. I didn't even get a chance to answer any questions, but if there's any questions, please email me or any comments. Maybe you thought it was boring or something. That's my email address there, clint@africateengeeks.co.za. So if you need something or you need to ask a question, please feel free to do so. I hope you guys enjoy your Saturday, and I hope to be able to help you next time. And if there is a particular topic that you would like help with, feel free to email me, and maybe I can try and fit it into one of the slots in the next 11 weeks. So thank you.